Hi everyone, welcome to our Module 4 Team Teach on Transformation, Symmetries, and Tiling. My name is Claudia Kemp.
I'm Jasmine Rodriguez.
Jessica Johnson.
Lolly Rodriguez.
Let's get started. Jasmine, can you show me the difference between a rotation and a reflection rigid motion?
Yes, Claudia, of course. First, let's look at the rotation. We will begin with our image on the left, and to create a rotation, we will hold the image in the center and turn it clockwise 180 degrees. Our rotation will look like this. Now let's look at a reflection. Let's create a reflection over a horizontal line through our center of the square. This will invert our trapezoid. Our square will stay the same, and both of our triangles will be flipped. And this is how our reflection will look like.
Cece, I noticed we reflected both figures on the right and on the left over the horizontal line. I know this because I can see the line of reflection in the middle of the squares, and it is a mirror image. Can you please explain to me what the name is before the reflection of the figure and the name of the figure on the right after the reflection?
Of course, Jessica, I can. Let me show you what I mean. First, the name on the left of the figure on the left is called an object because it is not reflected at the moment. The object, once the object is reflected, it becomes an image, as you can see on the right.
Jessica, can you explain what is a line of reflection?
Jasmine, I am glad you asked. If we take this image, add a line in the center of the orange tangram, and we will call it the line of reflection. This is called the object. When we have an object and when an object looks in the mirror, what do we get?
We get a reflection.
Right, we get a reflection. In geometry, it is also known as an image. Notice that the green tangrams are pointing in the same direction. They are just on the opposite side of the reflection line.
A reflection is like a flip then?
Yes, you are correct, Cece.
Cece, what is a line of symmetry?
Claudia, I'm glad you asked. A line of symmetry is the imaginary line where you fold the image in half and it matches vertically and horizontally.
Oh, I get it. So whichever side you fold, regardless of its horizontal or vertical sides, they both have to match, right?
Correct, Jasmine. Here are the three shapes given to us. Therefore, the hexagon, we could see that it has two lines of symmetry. If it's folded horizontally and vertically, we see that the sides match.
Now, Claudia, how many of these shapes demonstrate rotational symmetry?
Great question, Jasmine. I should be able to do this since you taught us what rotation means earlier. The basketball court can be spun 180 degrees and still look the same. Therefore, it has rotational symmetry. The star can be spun to a few different places and still be the same. And then the top left shape can be spun 180 and look the same. Same goes for the no symbol. It can be spun a couple times. And that one as well. So all of the shapes can be spun and still look the same except for the smiley face at the bottom and the arrow at the bottom as well. See the triangle? The smiley face can only go 360 degrees before it looks the same, and the arrow can go only 360 degrees before it looks the same.
Jasmine, what does a figure with symmetry look like?
Cece, I love your question. First, let's begin with a half circle. This image demonstrates one line of symmetry because we can draw a line of symmetry vertically, and both of our sides will look identical. As you can see, our left side looks exactly like our right side. Now let's look at our triangle. When we draw a line of symmetry vertically, do both sides look the same?
Yes, they do.
Well, that means that this triangle is also symmetrical.
Which of these figures has one line of symmetry?
Claudia, that is a good question. The shapes that have one line of symmetry are the rectangle, the hexagon, the rhombus, the semicircle, and both isosceles triangles. What is important to understand about line of symmetry is that when you place the line of symmetry on a shape and you fold the shape over, the line of the sides of the shape will line up, making it look like it has one shape. For example, if I place a line of symmetry on the rectangle, you can fold it over the shape, over the line, and the shape will look like a slender rectangle, or only half of the rectangle.
I noticed that all the sides match.
Right, Cece.
Well, just looking at the figures, I think that the rectangle, the hexagon, and the rhombus have more than one line of symmetry.
Jasmine, you are correct. But when you find one line of symmetry, then you know that the figure is symmetrical. Line of symmetry for the hexagon looks like this. And one line of symmetry for the rhombus looks like this. And as Jasmine mentioned, there are more than one line of symmetry for the hexagon and the rhombus. The rhombus's line of symmetry looks like this. And the semicircle looks like this. And the isosceles triangles look like this. Jasmine, maybe you can show me what a figure with no symmetry looks like.
Yes, of course. It only makes sense to show you both. Let's take a look at this figure. I will draw a horizontal line right through the middle. Do both sides look the same? No, it does not. Now let's draw a vertical line. Jessica, do both sides match now?
No, they do not.
Awesome. Therefore, this means that this figure is not symmetrical. Now we will look at our next figure. We will draw a vertical line, and we also see that both sides do not match. We will draw a horizontal line, and we also see that these sides do not match. Do you know what this means, Jessica?
This means that it has no line of symmetry, and therefore it is not symmetrical.
Awesome.
Claudia, do you know if it is possible for a shape to have no line of symmetry but demonstrate rotational symmetry? If yes, can you give me an example?
That's a great question, Cece. It is, in fact, possible for a shape to have rotational symmetry, even though it does not have a line of symmetry. Take the two shapes that Jasmine just showed us, for instance. We already know that they have no lines of symmetry, but they both can be rotated 180 degrees. So they have no lines of symmetry, but both can be rotated 180 degrees and still look the same as the shape before.
Is the figure shown a vertex figure?
Cece, that is an excellent question. The figure shown is not a vertex figure. Let me explain why. The interior angles of the figure has to equal 360 degrees.
We have 3 interior angles.
Yes, that is correct. We need to sum the interior angles together. If the interior angles equal 360 degrees, we have a vertex figure. If the interior angles do not equal 360 degrees, it is not a vertex angle.
I am sitting on the edge of my seat. I can't wait to see if this is a vertex figure or not.
The interior angle of an octagon is 138 degrees. The interior angle of a hexagon is 120 degrees. The interior angle of a pentagon is 108 degrees. Sum these together, and what do we get? 363 degrees, which is greater than 360 degrees. Claudia, are you disappointed?
A little.
Mm-hmm.
Jasmine, how do we calculate the measure of the central angle of the pentagon?
Good question, Jessica. First, let's review what a center angle is. It is simply the angle created at the center of a polygon. You create a central angle by joining 2 adjacent vertices of the pentagon at the center. The formula to find the central angle is 360 degrees, which is what it takes to go all around the center of the polygon, divided by n, which represents the number of sides of the polygon. And then in this instance, we have a pentagon, which means it has 5 sides. So our equation would be 360 divided by 5, which gives us 72 degrees. In other words, the number of central angles of a regular polygon will be equal to the number of sides of the polygon.
Thank you, Jasmine.
Cece, can you explain to me how I can find the degrees of the interior angles of such shape as an octagon?
Well, of course, Jasmine. The first thing that I have to see in order to know how to find the degrees of the interior angles is to find the number of sides. As we know, it has 8 sides. Therefore, we will use the formula n minus 2 times 180 divided by n, where n equals the number of sides. If we do 8 minus 2 times 180 divided by n, we get 135 degrees. Great question, Jasmine. Claudia, how do you find the measure of the interior angles of the shape?
That is also a great question, Cece. I will demonstrate it using this octagon over here. In order to find the measure of interior angles, we use this equation here. The value n in the equation represents the number of sides, which for an octagon is 8 sides. We then take that number, subtract 2, and multiply that by 180. We get 1080. This means that the sum of all the angles of an octagon equals 1080 degrees. How would we find the measurement of each individual angle?
I know.
What?
We would divide it by the number of angles, so you would divide it by 8.
That's right. We divide 1080 by 8, and we find that the measure of each interior angle is 135 degrees. Jasmine, can you give me an example of a vertex figure?
Yes, Claudia, absolutely. First, let's remember that in order to form a vertex figure, the combined measures of the interior angles have to add up to 360 degrees. This means that our figure cannot overlap or have a gap in between. We will start by using a dodecagon, which has 12 sides. We will use a hexagon, which has 6 sides, and a square, which has 4 sides. When we figure out their interior angles, we see that they're 150 degrees, 120 degrees for the hexagon, and 90 degrees for the square. When we add them up, they add up for a total of 360 degrees. This means that this makes a vertex figure.
Hey, Claudia, what triangle is congruent with triangle QPV?
Great question, Jessica. Triangle QPV can be seen here. A triangle that is congruent with this triangle would be triangle SPV here.
How do you know that?
Well, we know this because of the side angle side property, which states that if any pair of corresponding sides and their included angle are equal, then the triangles are congruent. The two triangles share one side, so that side is congruent, and they both have 90-degree angles. Therefore, the triangles are congruent.
Thank you. That's a great explanation.
Jasmine, are there any right angles in this figure?
Great question, Cece. How about we work this out together and see if we have any? First, do you know what a right angle is?
No, I do not know what that is.
Well, let me tell you. A right angle is the corner at which two perpendicular lines meet. They are formed by two adjacent angles that have a common vertex and a common side. This is how we know that angle QVP and SVP are right angles. We also know that they are supplementary angles because their measures add up to be 180 degrees. Since we have two angles, we divide 180 by 2, and we get that QPV and SVP are right angles with a measure of 90 degrees each.
Thank you.
Jessica, can you explain how triangle QPT is congruent to triangle SPT?
Yes, Jasmine, I would love to. Triangle QPT is congruent to triangle SPT because of the line segment PT is congruent. In other words, PT is like a line of reflection, meaning that the triangle SPT is a mirror image of QPT. Also, triangle QPT is congruent with triangle SPT because of the side-side-side theorem, which states that if the three sides of one triangle are respectively congruent to the three sides of another triangle, then the two triangles are congruent. How does the side rule apply to the given angles?
Excellent question, Jessica. First, we can see that angle Q and angle S are congruent. This means that both of those angles are exactly the same. They also share the same intersecting line P and T. P and T are congruent to each other as well. Therefore, this is why it is the side angle side theorem, because each side is connected to an angle all around.
Thank you, Cece.
Hey, Claudia, can you explain how angle QPT is congruent to angle SPT?
Yes, I can, Cece. Great question. These two angles are corresponding angles in two different triangles. We already know that these triangles are congruent, therefore their corresponding angles are also congruent.
Thank you, Jess. Thank you, Claudia.
You're welcome.
Jessica, can you explain to me how angles NOQ equals 24 degrees?
Yes, Cece, I would love to explain that to you. First, look at the equilateral triangle PQR and the midpoint O. From here, we can see another triangle. Inside that triangle, which is POQ, and this triangle has an angle that equals 120 degrees because of the central angle of the equilateral triangle is 120 degrees. Do you see the pentagon inscribed in the circle?
Yes, I do.
Let's pull the pentagon out and break it up, starting at the center of the pentagon.
I think I know where this is going. The interior angles of the pentagon must equal 360 degrees.
Yes, Jasmine, that is correct. 5x equals 360 degrees. Therefore, x equals 72 degrees. Since we have a bisector here on the pentagon, 72 plus 72 equals 144 degrees. That makes NOQ equal to 144 degrees minus 100 degrees, which equals 24 degrees.
Cece, can you tell me what an equilateral triangle looks like and what is the degree measurement?
Of course, Claudia. Let me show you how. Above, we can see that we have a green triangle, correct? Well, this triangle has three sides and they are equilateral because all sides are equal. This means that all the sides add up to 180 degrees, meaning that each angle should be 60 degrees.
Jessica, looking at this image, are there any similar triangles?
Claudia, that is a great question. Looking at the image, you would not think that there are any similar triangles, but there are. Triangles do not have to be the same size for them to be similar. The smaller triangle here is similar to this larger triangle here. Even though they are not the same size, they have the same shape.
Basically, we have a dilation where the smaller image has a size transformation to a large size.
Yes, Cece, that is correct. If we labeled our triangles, we would see that we also have congruent angles because of the triangles are similar. The smaller triangle is labeled ABC, and the larger triangle is DEF. Angle A is congruent with angle D, and angle B is congruent with angle E, and angle C is congruent with angle F.
Hey, Claudia, in that picture of the girl in the cliff, she is holding a ruler. Is there a way to determine how tall the cliff is from that far away?
That's a great question, Jasmine, and there actually is. First, we need to pull information from the original problem. We are told that the girl is standing about 1/4 of a mile away from the cliff and that the ruler is 2 feet away from her face. When looking at it, the cliff fits within a 1.5-inch span on the ruler. We will use these numbers and this relationship here to determine the height. So we have this equation here. We begin by plugging in our known values. Does anybody know what I need to do next to solve? After you can.
Oh, I know. You need to make sure they are in the same units.
Great, Cece. I'm going to convert all of the measurements into feet. Does anybody know how many feet are in a mile?
I know. It's 5,280 feet.
Exactly right, Jessica. 1 mile equals 5,280 feet. Therefore, 1/4 of a mile is equal to 1,320 feet. Like so. 1.5 inches is equal to 0.125 feet. We plug these new values into the equation like so, multiply both sides by 1,320, and we find that the height of the cliff is approximately 83 feet. Jasmine, what are the ratios of the triangles?
Thank you, Claudia. We know that in order for two triangles to be similar, the corresponding angles are congruent and the lengths of the corresponding sides also have to be equal. We determined that triangle CED is congruent to triangle CAB. These two triangles are similar because angle C is congruent to itself. We have angle E congruent to angle A, and we have angle D that is congruent to angle B. Since the triangles are similar, the ratios are as follows. Segment CE is congruent to CA,